Hello again everybody! In today's video, I want to introduce the concept of circular motion, and let's begin by building our vocabulary on the topic. When we talk about motion, we are going to talk about our position, velocity, and acceleration. Since we're talking about circular motion, these position, velocity, and acceleration are going to be differentiated by simply calling them angular position, angular velocity, and angular acceleration. Our angular position is just going to be designated by this theta, and the units are going to be in radians. And also, the shorthand version is just calling it rad. For angular velocities, we're going to deal with omega. The units for this are going to be in radians per second. And for the angular acceleration, this is just going to be an alpha, and this is going to be in radians per second squared. If we wanted to talk about the angular position anywhere on this circle that I've drawn here, now we would normally think that from one end to the other end, this would be about 90 degrees. However, in radians, we would always use a conversion. If we have theta in terms of degrees, then all we would need to do is multiply by pi radians over 180 degrees. This will give us our conversion from degrees to radians. Now there's one last term I need to talk about, and this is the period. Designated by a capital T, and this is in how many seconds was there one rotation. Alright, let's try to visualize this with some pictures. We're going to begin by talking about two different types of circular motion. The first is going to be uniform circular motion. This is when an object is spinning around without any increase or decrease in acceleration. So first let's draw our circle here. Let's begin by defining the radius, which is just a point from the center to the surface. That's just going to be r. Let's label a few things. Let's say from this point A to a different point, let's just say over here, B. The angle that it's going to make, of course this is going to be in radians, which is going to be defined by that theta. And let's say that this circle is spinning from A to B in a counterclockwise direction. We're just going to label that as omega. And let's look at a point on the surface that is tangent to the circle. If we look at a point over here, let's just say point C, the velocity that's tangential to this point C is going to be pointing downwards, and it's going to be the velocity. The tangential velocity, let me make that a little bit more clear. And then it is always going to be accelerating inward toward the circle, and that is going to have some centripetal acceleration. The centripetal acceleration and the tangential velocity is just what keeps a point on the surface to keep spinning around in the circle. Now if we look at non-uniform circular motion, this is when we were going to have the thing that is spinning either accelerating or deaccelerating. Once again, if we look at a point tangential to the circle, and again, let's just say that it is spinning in this direction with omega. Once again, there is going to be a centripetal acceleration pointing inwards towards the circle. Then there is going to be a tangential acceleration. And finally, we could just say that this is the regular type of acceleration we would all think about. The direction and magnitude of the acceleration is simply determined by the centripetal acceleration and the tangential acceleration. It's more or less using the Pythagorean theorem, which is just acceleration is equal to the square root of the centripetal acceleration plus the tangential acceleration squared. Now when we talk about circular motion, there are going to be a lot of different terms that we need to cover. So let's just begin. Now if we're going to talk about some circle, from point A to some point B, this distance, I'm simply just going to find that that distance on the surface is an s, so therefore theta would be s over r, where r is just the radius. The tangential velocity is just going to be the angular velocity times the radius. The period is going to be 2 pi divided by the angular velocity, or another way written, if we just plug and play, it's 2 pi times the radius divided by the tangential velocity. The centripetal acceleration is going to be equal to the tangential velocity squared over r, or rewritten, that would just be the angular velocity squared times r. And last but not least, the tangential velocity is equal to the angular acceleration times r. But hold on a second, we haven't talked about the angular acceleration. The angular acceleration only happens in non-uniform circular motion. Now let's describe a few of the circular motion kinematic equations, or their equivalents. Now if you look at the equations of motion for circular motion, we're going to see that these are very, very similar to linear kinematics. Again, the position is replaced with a theta, the velocity is replaced with an omega, and the acceleration is replaced with an alpha. And literally everything else is the same. Now, let's look at an example just to make sure that we understand how to use all of these equations. A pulley with a radius of 1 centimeter is rotating at 1,000 rotations per minute and is slowed down to stop spinning in 1 second. What is the tangential acceleration at its surface, and how many revolutions did it spin during this time? Well, let's try to find out what we have so far. We have the radius, and it's telling us it's 1.00 centimeters. We have the time that it takes for it to stop. That's t equals 1.00 seconds. And for the period, we have that as well. It's just 1 over the RPM, and that is, we have to do a little bit of conversion since this has to be in terms of seconds. So 1,000 rotations per minute, or there we go. And then we have to multiply that, because for every 1 minute there are 60 seconds. Okay, we have all of that so far. And we have everything we need to solve for the angular velocity. So it started out with an angular velocity of 2 pi over the period. And from here on out, I'm not going to be writing the numbers down other than the results. So let's see what we can do here. Now we are trying to solve for the tangential acceleration, and that is equal to alpha, the angular acceleration, and times r. So we need to solve for the angular acceleration. Let's try doing that with one of the kinematic equations, shall we? Since we have the angular velocity and time, and we want to solve for the angular acceleration, let's use this following equation. The final angular velocity is equal to the initial angular velocity plus an alpha times t. Now the final velocity, we know that to be 0, or angular velocity, that's 0. So solving for alpha, we would get negative. There we go. Okay, now let's get this back into the tangential acceleration, because that's what we're initially solving for. So let's just start plugging in what we have for alpha. Negative omega divided by t times r, and then we can substitute omega for negative 2 pi r over the time times the period. And once we do all of these calculations, if you just want to make sure for yourself, we would get negative 105 radians per second squared. And it's a negative sign because it is deaccelerating. Make note of that. Alright, let's move on to the last part, which is to see how many revolutions did it make during this time. For that, let's use another circular motion equation. Let's use this one. Omega f squared equals the initial plus 2 alpha delta theta, and we are solving for delta theta. The change in the angular position would be negative omega squared over 2 alpha. And again, once we substitute this, we would get omega t over 2. And substituting one more time, this would be 2 pi t over 2 capital T, that's the period. And once we solve for this, we would get 52.4 radians, if you want to make sure. Okay, that does not necessarily give us the information that we want to answer this question. We want to find out how many revolutions did it spin during this time. We have the radians that it span, but now let's take that number and convert it one more time. We're just going to call this revs for revolutions. And that is equal to the change in the angular position over 2 pi. And let's just say that this is going to be in units of radians per rev, just to make this a little bit more easier to understand. And the total number of times that the pulley span was 8.33 revolutions. Revs. And there you have it. We've learned a bit of the vocabulary. We've seen some diagrams of what this circular motion would include, and we've seen an example. Hope that helped everybody, and good luck out there.